So we are doing the chapter more on sets, and we have defined the definition of union, intersection, and then we have defined a proposition for the De Morgan's law on union and intersection, similar to that. Then we have defined some notations for the union and intersection for the finite and infinite states. Then we have defined the Cartesian products, and we have defined the proposition which is for the order of A union B. Now we are going to talk about the inclusion exclusion principle. And that is if A1, A2 up to AN are finite states, then the size of the union of all these states can be calculated by adding together the sizes of all intersections of an odd number of these sets and subtracting from this the sizes of all intersections of an even number of sets this can be proved by using the induction. Now you can ask some question that how many integers are there between 1000 and 9999? that contain the digit 0, 8, and 9. At least once each. Okay. For example, 8950 8089, and something like that. So solution, say that late S is a set which is 1000, 1001 up to 9999. Now for K is 0, 8, or 9, let AK be the set of integers in the set S that have no digit equal to K. Then A0 union A1 union A8 and union A9 is the set of integers in S that are missing either 0, 8, or 9. And so the number we are asked for in the question is that what we do the order of the set S minus the order of A0 union A8 union A9, which is 9000 is the order of set S minus the order of union A0 A8 union A9. Now we therefore need to calculate the order of this set, which we shall do using above equality for the union A union B union C. By the multiplication principle 16.1, we have, so we need to find that A0 union A8 union A9 is what? And then by multiplication principle 16.1 in previous chapter, we have A0, A9 is equals to 8 cross 9 cross 9 cross 9. Since there are 8 choices for the first digit, it cannot be 0 or 9, and 9 for the each of the others. So similarly, we have a number of A8 is 8 cross 9 cross 9 cross 9. So those are 5, 8, 3, 2. A0 have the order as A0 9 cross 9 cross 9, and that is 6, 5, 6, 1. Now we know that A0 intersection A8 have the order equals to A0 intersection A9, and that is 8 cross 8 cross 8 cross 8, and that is 4096. And we have A8 intersection A9 have order 7 cross 8 cross 8 cross 8, and that is 3584. And similarly, all of them have the intersection as 7 cross 7 cross 7 cross 7. So that is 2401. Therefore, by this 17.1 equation, we have the order of A0 union A8 union A9 is equals to with all of these numbers 8850. So the order of S, which has that, or should I say that hence the number of integers in the set S that have at least one of these digits, one of each of these of the digits 0, 8, and 9 is equal to 9000 minus 8850, which is 150 only. Quite a surprising number, very short one. Now we will give a very nice and famous kind of proposition for the number of possible subsets for a set. (17.3) says that let S be a set, a finite one, finite set consisting of n elements. Okay. Then the total number of subsets of the set S is equal to 2 power n. And we will prove this theorem, this proposition, and then we will end this part of the lecture. So let's say let S is a set which contains n elements. Okay. Let's take a subset which has I1 to ik elements of S corresponds to a string consisting of n zeros and ones, where we put ones in positions I1 to ik, and zeros elsewhere, and every such string corresponds to a subset. Okay, so for example, if n is 6, the subset is 2, 3, 5, corresponds to a string string 0, 1, 1, 0, 1, 0. Okay, so 1 at the position 2, 3, and 5, and the string 1, 0, 0, 1, 0, 1 corresponds to the subset 1, 4, 6. Hence, the number of subsets of S is equal to the number of strings consisting of n zeros and ones, since we have two choices, 0 or 1, for each of the n entries of such a string. The number of strings is equal to 2 power n. And that is the proof of our proposition. You hardly see a proof for this kind of proposition in a set theory. So enjoy. Thank you.